Okay, so now we should be live on YouTube also.
Okay. So yeah. So we had this general bound. So like due to Kramer-Chernoff holding, as we say, all of I think initially Kramer and Chernoff started using this kind of a method. And this, of course, this looks a little bit like the Legendre dual, but it's not exactly the same. But it is similar. So then we started looking at, okay, what can these functions look like? These Vx of t, and one example we looked at was something called sub-Gaussian random variable. So a random variable x is supposed to be sub-Gaussian with parameter nu bigger than 0 if this phi x of t, this log moment z function, is less than nu t squared by 2. So it's dominated by a quadratic function. Okay. So for such functions, and this will show include Bernoulli and Gaussian. That's why that Gaussian is where the name sub-Gaussian. So the tails are not heavier than the Gaussian. That's the point of sub-Gaussian. So for such functions, let's try to see what this Kramer-Chernoff technique tells us. So you have to compute this supremum of PA minus this log, right? So that, because phi x is less than is nu t squared by 2. So this is at least, so this is bigger than alpha. So I am substituting something that is less than phi x. So I get greater than equal to greater than supremum of t bigger than 0, alpha t minus pt squared. So this is a standard quadratic approximation. You get alpha squared by 2 nu. Right? So the optimal t gives you this value. So you get that if x is sub-Gaussian parameter nu, then the probability that x is bigger than alpha for any alpha. So here I think I assume that actually I didn't. Yeah, so I sort of assume that alpha is 4. So it's but it's fine. I mean, if x is sub-Gaussian minus x is also sub-Gaussian, you can show that, and therefore it's easy to show that. And so you'll get bounds. But yeah, so this we get probability that x is bigger than alpha is less than exponential of minus alpha squared. So the point is it goes like a square in the deviation and 1 over the sub-Gaussian parameter. That's the important thing to keep in mind. So it's square of the deviation. Okay? So that's like the Gaussian. So the probability the Gaussian is bigger than some large number t is sort of like e to the power minus t squared or e to the power minus order of t squared. So that's why this is called sub-Gaussian. So in the homework, you will do one thing where you will get something slightly weaker for large t. So this I think will also be discussed last class, that if you take the square of a sub-Gaussian random variable, then you might only have something weaker instead. Okay, so the point of this for us though is that bounded random variables, such as Bernoulli random variables, they're bounded. They're absolutely bounded between 0 and 1. Bounded random variable is nice. So it's Hopding. So this thing called the Hopding bound. This says that the random variable which takes value only in the interval a to b, a and b are real numbers, is sub-Gaussian with parameter. Okay, so actually, so I define sub-Gaussian with I define sub-Gaussian with for arbitrary random variables, but usually what you do is you center the random variable first. So you take x minus the expectations, that mean is 0. So that's just technicality. We'll come to that later. But the point is that any thing like this will be sub-Gaussian parameter b minus. So something that depends only upon the size of this interval, square by 2. Actually, the correct thing is 4 here. So you get even better than this. The proof I will do, I think we only get 2, but you can do something slightly better to get 4. Here. Okay. Right. So but assuming this thing, we saw that we are in good shape, because if I look at x is Bernoulli p and I just look at x minus p, so it is a mean 0 sub-Gaussian variable with parameter 1/2 just by applying this Hopding bound, right? Because its values are bounded between minus p and 1 minus p, so b minus a. And so by this method itself, when x so our xi were ideal. Yeah, okay. So no, so this by itself was not enough. So with this by itself, what we could use is that so if I just use this bound for the full sum, all n of them,
then my interval becomes larger, right? So it was right now it was of size 1, now it becomes size n because I'm just summing up n things. They could all be at the same time.
so that would not be good. That will give us sub-Gaussian parameter n squared by 2.
But that is not using the fact that these exercises are independent, right? There's just that they're bounded.
So the crucial point, and this I asked you to do as a homework, it's easy,
And I hope everyone has done it.
is that if x1 to xn are sub-Gaussian with parameters mu1 to mu1 and they're independent, then the sum is sub-Gaussian, just the parameter is the sum of these sub-Gaussian, not square, but just the sum. So here it became n squared. So,
So this is where we were, okay? And yeah, and this is easy. This is just from the definition. You just apply the definition and you get it.
so for us, this would mean that that summation xi I one minus p is sub-Gaussian with what? With what parameter?
n by 2.
Yeah. So the crucial point is that it's n and not n squared. And now if you substitute into the bound, you will get something else. So this would imply that the probability that summation xi is bigger than p plus epsilon times n. This is the same thing as the probability that I going from 1 to n xi minus p is greater than epsilon times n is less than yeah. So I just apply the rule. So exp minus the deviation, which is the epsilon squared n squared. So that's the point. So there's a square that's coming just from a deviation divided by this sub-Gaussian parameter, which is so n by 2 times 2. Okay, and this will be less than minus n epsilon squared. Okay. Yeah, actually, yeah. So the correct answer is that this should be 4, and then this would be n squared, and then this would be n, and then this would be this. Wait, what am I doing? Sorry, I went the wrong way. This would be n squared by 4, and this would be n by 4, and this would be n by 4, and this would be 2n squared. This factor doesn't matter so much. The point is that it's again the epsilon squared here, which is a relative deviation, and n. So the more the number of samples, the better you get for the same relative deviation. Okay. The same relative error epsilon, the more the number of samples, your error is now decaying exponentially n. Earlier, these things used to be like 1 over inverse polynomial n with Chebyshev, etc. Now it's exponential. Okay, so that's where we are. So let's start with. So. Okay.
Piyush, can you go back
Uh-huh.
to the last slide? You wrote down that the summation xi minus p is subversion with parameter n square by 4.
Sorry, your voice is not clear at all.
Hello?
Yeah.
So you wrote down that by using Hovding's bound,
Mhm.
summation xi minus p has parameter, subversion parameter is n square by 4.
Yeah.
How this 4 is coming into the picture? Oh, okay. It's
Well, yeah, I use the actual Hovding bound, which is actually 4. What we will
okay,
do
okay,
will
okay,
probably
fine.
be just 2, but I
Okay,
mean the 4
okay.
is not so important. The point is how is it, like the square is important, and
Yeah.
yeah, I see which proof I do, but yeah, but depend. Yeah, so there's arguably the simpler proof gives you b minus a squared by 2, and the slight is more complicated. So yeah, so now, so yeah, so so what we have so far is that there are these x's, the which is the indicator of uh, gi is bad, okay, so let me see the notation right. So I think the final estimator I call it g, right? Yeah, m is the mean only. So and that, and we define m to be the median of g1 to gk, gi independent, right? And yeah, and what we had is that the is a, so probability so rather the expectation of each xi was less than 1 over 8, and the probability that m minus f2 is bigger than so the same epsilon, so which is that the median is bad, uh, was less, so it's less than the probability that the summation xi is bigger than something like so it was k plus 1 by 2, but let me just use k by 2, so which is even worse, right? So we and this now we can analyze with the previous thing. So this is the crucial thing by the previous bound. So this is what, so this is now so what is epsilon here? So that's the only thing. So this is in two steps. So probability this one k xi minus, so each one was like 1 over 8, right? So let me call this p. So it is less than 1 by 8. So p is greater than k 1/2 minus p. Right? And so this whole thing is less than exponential is minus 2 times k times half minus p squared. So this comes equating off. But we know that p is at most 1 over 8, so this whole thing is less than. So what is half minus 1 over 8? 4 by 8, 3 by 8, right? So 3 by 8, 9 by 64. So something like 9k by 32 or something. Let me just make sure that I have the constant right. Yeah. Okay. So now, yes, what was our goal? Our goal was to drive this probability. So what we wanted to drive this. So we wanted that the probability that m is bad, that m minus f. So our final estimator is m, right? That median. So the probability that this is less than epsilon f2 is less than delta. So we want to make this thing less than delta. So so, so from star, this requires
Greater than epsilon f2, right?
Greater than, right?
oh sorry. Yeah, good. So k bigger than something like 52 by 9 log 1 over 2. So the crucial thing now is that this is now the error probability is now depending upon the log. So the number of samples you need is like log of 1 over the error probability. So it's growing slowly, right? So earlier, so if our errors, if our error probabilities were like 1 over n squared, to make the probability 1 over delta, we need to make about 1 over square root delta samples. Now it's only log of 1 over delta. Okay. So this is the final thing. So what we have gained. So what we have. Oh, so what we gained is that only O of log 1 over delta samples of the GI are needed to drive the error probability to below delta. So there are two kind of error parameters. One is an accuracy parameter epsilon, the other is the error probability delta. And now let's just see how many, what is our total storage or work or whatever so far. So there were two things so far. So summing up, each GI was also something complicated, right? What was each GI? How was that obtained?
Average of yi's.
Sorry?
Average of yi's.
Yeah, so let's look at this. So fix epsilon positive, which is the accuracy parameter. Right? And delta is the error probability. Error probability tolerance. Okay. So yeah. So what did we have? So we had that. So there was an M, which was something else, right? There were too many M's now. So okay. So then what we have seen so far that if our stream is over d dimensions, right? Then each yi, so there were these yi's, let me call them yij, right? Each yij was defined as j equal to 1 to m, 1 to d, no sorry, k equal to 1 or l equal to 1 to d of the frequency of the lth element in the string times this u ulij. Okay. So and what was the thing? So the requirement was for fixed L, for fixed ij pair. So yeah, so here FL is the frequency of the LS element.
So there's a square term missing, right? I mean, it's the summation square. Right?
Oh yeah, going to be square already. Okay. yeah, so nth element. So for a fixed ij pair, what we needed was that the collection ulij l equals 1 to d is what?
Four-wise independent.
4 ways, yeah.
Yeah, 4 wise independent. L random L uniformly random. Oh, plus 1 minus with expectation 0 is 4 okay, this okay, you cannot do the light for it. 4 yeah, I think also there's some okay. Okay, so yeah, so that is okay. And okay, so far so good. And now what was this? So this was the first step. Second step was defining these GIs. So each GI was a summation of j going from 1 to s, ij, and then taking a mean, right? And on this, we only require that these ought to be pairwise independent, but let's assume that they are actually independent. So yeah, so this was how the GI was defined, where s had to be bigger than. So we had something like 16 over epsilon square. Right? And so what we have is that for yeah, so across these things, right? So we needed yij fixed type j from 1 to s fixed to be pairwise, at least pairwise independent for this. So yeah, so but let's be sort of generous and just assume that so this is achieved by ensuring. So let me do this later. Once we have done that. So this is one requirement, and then finally the third step was taking m to be the median of g1 to gk, and where k is bigger than some 32/9. Okay, and again at this time we need g1 to gk to be fully independent. Okay, so both this is the second requirement, and both both 1 and 2 are fulfilled. Okay, how do we start? Let's correct it. Fulfilled. So, if we assume that the vectors is 1 to what is that? 1 to 3 as ij vary are independent. Right? So we have this vector of size d, where the random bits inside the vector are supposed to be fourwise independent, but the vectors themselves are just fully independent. How many of the vectors are there?
One by epsilon square log 1 by delta.
Yeah, so
Okay.
that times k, which is like odd by order of 1 over epsilon square times log 1. So, okay, so this is where we are so far. So right now, what is the storage with what we know so far? How much storage do we have? So we have to store all the yi's and all of these. So what is the total storage for yij, gi, and m? So really, you only have to store. So the gi etc. are just summary statistic, right? So the storage is for the yij. So the storage of the storage requirement for so we have this. We have O of this we have S times A, which is O of this we need epsilon square log counters. Yeah. So no dependence upon D at all. It's so far. So that is some storage, right? So we need storage for this. But there's something else also we have to store, right?
The random bit.
Yeah, we use the random. We have to store the random thing. And if we just do it naively, each vector is of size d, and there are rest. But if we make all the u, l, I, j independent, we will have to store theta omega, and this is a good point. Wait, sorry, let me just so I think these things get cut off in the b times 1 over epsilon square log random bits. But that will defeat the whole purpose. The whole point was to save on this d. D was supposed to be very large for us, right? But the whole point of this exercise was to not need storage that grows linearly in terms of the alphabet size of the string. How many distinct kind of letters? Because D was the thing that was supposed to be large for us, right? How many different kind of tokens can you see on the string? And in any case, if you are allowed to use order D storage, then why just keep an associative array, right? Like just a map, hash map, or a binary tree based map, or a balanced binary tree based map. Just store the counters. Right? So why go through all this? Set of use? Who's an associative vector? So yeah, so if you, in your favorite library, you might be called hash. They might be implemented as a hash map or a balanced binary. Balanced binary tree. Okay. So the point is to get rid of. So how do we get rid of this D? Okay. Yeah. So that's the question. So how do we do that? So what? Yeah. So what is the thing? So what? Where can we save? So the only thing that we. So where can we save? So this 1 over epsilon square log 1 over delta will be there, right? I mean, we have these many counters. So what's the only point where we could possibly start doing something? So, I mean, it's clear that we do not want to store all these random bits, right? So somehow we have to be able to have a succinct description of some of them. So which of them? So maybe so I learned this trick recently. So there's a raise hand feature I think in Zoom. So all of those who know the answer should raise their hand, or whatever, push the raise hand button on Zoom. Although I don't know how to see it. Okay, although I do not know the answer, should raise them. Okay, so we have one. Okay, so I mean, it's underlined there, right? I mean, we do not need them to be independent. So we do not need inside this each vector. So there are these s times k vectors. Inside each vector, we only need the bits to be 4-wise independent and not fully independent, right? So somehow we have to use the fact that there are only limited independence is needed to succinctly describe the bits. Okay, so we need to use we need to use that each of the S arrays only needs to have 4-wise independent and not fully independent. That's a question. And not necessarily fully independent. Bits. Well, they're not bits; they're signs. But so Rami also is writing. So we instead of so we don't even need to compromise. We already knew that we only need 4-wise independence, and that's so for people who work in computer theory, it is all extremely trivial, but it's think of it from first principle. It's a very nice idea. So, okay, so now, so how can one save this kind of thing? So instead of 4 ways independent, let me first look at 2 ways independence and see how it's very easy to see, or okay, it's a very simple construction which lets you store n uniformly random bits, each of which is uniform, which are pairwise independent, using only log n storage. So you will have a system which will store only log n random bits, you actually truly uniformly random bits, and using that, it will, if you ask it for any like the 1 to, so ith random bit where I can go from 1 to n, it will generate the ith random bit in such a way that the I and jth random bit, when I and j are different, will be pairwise independent. Will be independent. But if you take 3 of them, they won't. Okay, so they might not. So what is this? So yeah, so let's look at. So yeah, so limited independence. So what do we want? So what we have, so what we want is a system like this. So there will be some. So we only want to store the short seed. So a small number of truly random bits. This is called a seed. I hope I'm using the right terminology, but seed is right. Seed is okay, right? Yeah. So yeah. So seed and yeah, and such that a deterministic algorithm working with the seed can produce a much larger sequence of bits which look, say, pairwise. So say pairwise independent, to an outside observer who has not seen the seed. Okay, so seed is chosen completely at random. The definition of the outside observer is that the outside observer should not have seen the seed. Seed is random for the outside observer. Over that randomness, the algorithm is completely deterministic. It will take this random input, then do deterministic thing. The outside observer will ask me, give me the first bit, give me the second bit, give me the third bit, give me the 10th bit, give me the nth bit, so on. And the algorithm will produce these n bits. And of course, it will produce this different sequence of n bits depending upon the seed being different. And the distribution that the algorithm's output has, the only randomness in the algorithm coming from the seed, will look pairwise independent to the observer. So it's yeah, let's just do this by example rather than going to the philosophy of this. So yeah, so this construction is actually quite simple. So so here is a construction. So let's say we store as seed x1 to xn sampled independently, so completely independently. And uniformly at random. So let me call this x, or let me use s. S1 uniform at random. 1, 0, 1. Right? Sample uniformly at random. So if I sample n bits uniformly at random from 0 to 10, they are also independent. Okay, now what is the algorithm? So the algorithm, so the outside observer will ask the algorithm for a particular bit state. So when the outside observer asks for a bit I where 0 is less than I is less than equal to I is less than 2 to the n minus 1.
So the algorithm is not prepared to give out 2 to the n bits. It stored a seed of n bits and it's prepared to give out 2 to the n bits, 2 to the n different bits with different indices. Bit indexed I where okay again this would be the algorithm outputs a s I, which is defined as XOR. So XOR of bits as with j going from 1 to n of si sj times the indicator of whether the jth bit of I is 1. So it's pretty simple. I just look at the binary representation of I, look at all the positions that are 1, just XOR those bits of my seed and give it to the outside observer. So the outside observer gives me an index I. I look at the binary representation of I, look at all the bits that are 1 in the binary representation, XOR the corresponding bits of the seed and give it out back to the outside observer. And the claim is that so what is the claim? Claim is the probability that for every ij, I not equal to j, 0 less than I, j, this is less than 2n, so less than equal to 2n minus 1, less than equal to 2n minus 1. So the n bits in the representation. The probability over s chosen uniformly from 0, 1 to the n. So ij are not random, only s is random. The probability that asi equals alpha and for every alpha beta in 0, 1 and asj equals beta is in fact equal to the product of the probabilities. And each of those is is 1/2. Crucial point is that I not equal to j, of course. I mean, otherwise, but the point is this shows that the output of the algorithm over the random seed is pairwise independent. This is the definition of pairwise independent. So there are these sequence of bits, I going from 0 to 2 to the n minus 1. And the algorithm has chosen and stored forever this random seed. And now if I keep asking the algorithm for these things, the distribution of that is induced by this algorithm on these 2 to the n bits is pairwise independent. So what have we done? We have stored n bits and now are able to produce 2 to the n pairwise independent bits. Should I prove the claim, or is it clear, or should it more be like homework? So how would you go about proving this? Let's see. Yeah. Maybe I won't write the format. I mean, it's not hard. Yeah. So the only crucial point to notice is that when I and j are different, there will be at least one seed bit that appears in I and not. I mean, that is, so it cannot be the case that the set of bits I, so the set of bits that you took the XOR of is the same for I and j. Right? I mean, because I and j are different, they have different binary representations. That's why we could only go up to 2 to the n. I mean, beyond that, like the bits after the nth position will not matter, so we start repeating. But here, for these I and j, they must differ in the first n bits of their binary representation, and therefore and that by itself is sufficient to get this. I mean, actually, what we prove directly is that this number is actually equal to 1/4, and that would imply the middle equality also. Okay. So this is pairwise independence. Unfortunately, at least I don't know of a method to generalize this version to fourwise independence. Is there one? So I'm going to do a different construction for the fourwise thing. First of all, I don't know who is this due to. So like Prahlad or Ramya or complexity or Rajat or
Who is what due to?
This one, this construction is
This
probably
matrix sort of construction. This matrix sort of construction.
Yeah. But this is probably from coding theory where people have.
Yeah.
Yeah.
Also, should I be like greater than 0?
No, no, that's fine. I see what you're saying. Yeah, that is a good point. Yeah, so that is really a good catch. So one way of fixing this is I'll actually store n plus 1 bits. And I will just add a 0 to everything. Now everything.
I don't want to remove 0, so I just do this. So now everything is uniform. So even the only problem was that the 0th bit was just fixed to 0. So I equal to 0 is fixed to 0. So this claim as stated was false. But now it's not. So everything is random, and so each of these properties is now 1. Okay. Yeah, so I encourage you to prove it. I mean, it's the simplest way to prove it. We just just factorize this conditionally, and then use the fact the condition doesn't matter because of this difference, and the fact that there will be some bit that is present only on one side, only in one of the ions. So you either prove that this is half first, each of these is half first, and then use the conditional probability because the conditioning doesn't matter. So yes, the second thing I was saying is that I don't know how to generalize just this kind of thing to fourwise. So for fourwise, we look at a different perspective, which is nice. So so all of these things relate to codes. So this one I think is just what is called the Hadamard code, right? I'm not sure. But the second one will also relate to a different class of codes, but we don't need to know that. It's sort of like how the polynomial-based codes like Ritz-Roman, etc. work, but we don't need to know that. We'll just use a simple property that is also used in the coding setting, but that's what we'll do. So I hope everyone is familiar with the finite field. It's okay.
So Piyush, this pairwise independent, I think, is core gold, right? But certainly it existed much before them.
What is the spelling? What's the spelling?
Chor or Chor and Goldrake, yeah.
Okay. And this one I think is at least as old as BCH. But again, maybe not written in this way. Even Hilbert. Yeah. Okay. So the second construction of general k-wise independence And these won't be bits though. So general QA is independent, some random variable. So that will be a bit annoying, but we'll see. QA is independent. QA is independent random variable. Okay. So what we'll do is fix a finite field there. So what is a finite field? Okay, let's have a, this one. I think we should have a show of hands. So how many people know what a finite field is? Three, four, five. Okay, so that seems to be a reasonably large number. Okay, so maybe yes, maybe I'll just mention it. So okay, so the finite part, let's forget about it. A field is just a set. So so a field is just a set with a with a with a zero element, a one element, different from the zero element. Zero element, commutative addition and multiplication. And of course, the zero element is the identity for addition. Oh, what is reactions? Oh,
No, no, no.
Oh,
That was
okay.
next to how to raise hands.
Oh, I see. No, I know Rajat knows what a finite field is. So you don't need to raise. Yeah. Just a second, commutative addition. With I'm pretty sure I'm missing some condition with multiplication and distributing over addition. So basically, just think of real numbers or complex numbers distributing over addition, in which every element except zero has a unique multiplicative inverse. And every element has a has an additive inverse. Okay. So an example is complex numbers, real numbers, rational numbers. Non-examples, I think is more useful. So what are some non-examples? Maybe one of the people who did not raise hands. Say what a non-example is. Ishant, maybe?
Integers.
Integers, yeah. Or matrices. Let's say inverted, yeah, so because it won't be commutative. Okay, so what is a finite field? A field that is finite is a finite field. That seems like a very facetious thing. A field with finitely many elements. So this looks like just some thing. It looks like all the interesting examples will be infinite, but that's not the case. This is a very so it's not. If it's immediately obvious to you, please tell me how it is. But it's an important result that any finite field has size has
size p to the d for some p prime, including 2, not odd, including 2, and b a positive integer.
So these are all the finite fields, and in fact, this is exactly one. And further, there is exactly one. So what does this mean? This means that all of them are isomorphic. So in the right sense, okay, one finite field. Of each subset. So they are actual objects. So these objects are all like they are like as real numbers, complex numbers. Yeah. So, but the crucial thing I would need about finite fields is that they have this property of sort of Lagrange interpolation. So the thing is that you can, yeah. So this is fine. So one can define polynomials over finite fields. Okay. I mean, just as usual. So let's consider if so and what is a polynomial? It's just, I mean, like this, right? So each alpha I is in F, right? And x is some variable. The crucial thing is that Lagrange interpolation, Lagrange interpolation works in the sense that if that for every so there is this, or rather maybe even more basic than that, any two, if p and q are polynomials of degree d over f, and p beta I is equal to q beta I, for d plus at least d plus 1 distinct beta I in F, then P is equal to Q. So the polynomials P and Q are equal. And this is exactly the same proof that you would do on over the reals of the complex numbers. Basically, you get a system of linear equations, and it has full rank because it's the determinant is a von Neumann determinant, and therefore you get that the alpha is a complete determinant by giving the values at d plus 1 of d. So basically, a polynomial is completely determined by giving its value at d plus 1. Of course, because a finite field, d cannot be too large. I mean, there are only so many points in the field. But let's not worry about that. This result is just true. It's just that the polynomials of degree higher than d sort of are not quite polynomials of degrees higher than d when seen as functions. Okay, but yeah, for us that won't be an issue. So this is the crucial fact. Okay, so let's just wait for a second on this. So what is it saying? It's saying that if I have a polynomial of degree d, it's uniquely determined by
So yeah, so there's also implicit in this is also the fact that if I have a polynomial of degree d plus 1 and I tell you its value at d points, you know nothing about its value at d plus 1 point, because this implicit in this that you can also invert the polynomial, because there is always a polynomial which, so if I take d plus 1 values, yes, maybe I'll just write as a separate fact. D plus 1. This I will. Okay, if alpha zero to alpha distinct values and beta 0 to beta t arbitrary values, and then so there always exists. So this you can just do the exercise. Always exists a polynomial p such that p alpha I is equal to beta I, 0 is less than or less than t. And this polynomial must be unique. Is unique by the previous fact. So considering the polynomial is not hard. It's just usual Lagrange interpolation, and just as in the proof of the Lagrange interpolations, first fact implies that this polynomial is actually unique. So the upshot of all of this is that if I have a degree d polynomial and I give you its values at d or fewer points, you cannot say anything about its value at a distinct point I give you later, because there is always one polynomial that will agree at d plus 1 points. So you can always draw a polynomial of degree d through d plus 1 points. Right? I mean, that's the thing. Yeah, so okay, so now the crucial thing is this, that that if I now take what is the construction of our so after all this, what is the construction of our thing? So here's the thing. So ky is independent elements of f. So let's say k is less than log of the size of f. Q is independent and taking values in it. So how do I do this? So what we do is pick. So construction. So the construction is pick alpha 0 up till alpha k or k minus 1. K minus 1. Alpha k minus 1. Again, uniformly at random, just like before. So this is a seed from it. Need not be distinct, just uniformly at random, k elements, alpha 0 to alpha k minus 1. So this is the seed. And now what are my values? How so? Okay, so now what is this is the seed, right? And now the outside observer. So what I'm going to produce is size of f many elements. Okay. Outside observer inputs, some x or some, let's say, gamma in f, and the algorithm with, so this, let's call this alpha vector, a alpha gamma, the algorithm outputs algorithm outputs
You-
what? Yeah.
Yeah, we need one more thing. We need that we can lay our hands on the field F.
Yeah, so that will come to later. Yeah.
Okay, okay.
Yeah, in fact, I will show them code for a bit.
Okay, fair enough. Okay, good.
Yeah. Yeah, so what Prahlad is pointing out, so I'll write down something and then we'll try to make sense of it, and that's what Prahlad is pointing out. So what we will do is we'll just do this alpha gamma to the I and alpha I gamma to the I. Yeah, so what Prahlad was pointing out is that, yeah, so this is what algorithm output, but the algorithm needs to be able to do these computations, right? So it has to have some representation of the field. It has to know what gamma is. It has to then be able to compute from gamma squared, gamma cubed. It has to be able to multiply two elements in the field and give what it means in the field. So this it has to be able to do. So yeah, so we'll have to see how to do that. But for now, suppose that all it is available, then this is what the algorithm does. Right? So it has chosen the seed. The seed was alpha 0 to alpha k minus 1. Basically, what algorithm is doing is it has defined a polynomial using the alpha as the coefficient. Whenever it gets this, the outside observer asks for a particular random element of f, indexed by f, so gamma. The algorithm just evaluates the polynomial on gamma and outputs the number, which is also a number in gamma. And now the crucial thing is that that these are that now the point is that the probability that 1 over I equals 1 to k so I'll write back this claim. So claim that gamma 1, gamma 2, gamma k in f be distinct, and then and beta 1, beta 2, beta k in f arbitrary, and then the probability over this alpha being chosen uniformly at random that, so this is like noticeable and, so the probability that all of these events hold that, so right, so, right, this is just the product of these corresponding products. Let me call this G, just to avoid confusion. Okay, which is just 1 over F2. So actually what we'll prove is just this fact, and the middle equality again follows. Okay, but we've already proven this more or less. How have we proven this? Well, what is this? This is asking for, so basically is the choices over alpha, right? How many possible choices for alpha are there? What is the total number of possible choices for alpha?
Size of f.
No, size of f to the power k, right? Because there are k of them.
Oh, okay. Yeah.
So and what we have shown is that, so this claim is exactly like a cryptic sort of a hidden version.
Yeah, okay. So it's just a cryptic version of these two facts, right? Yeah, so let me just so these two facts combined together say that there is exactly one polynomial of degree d that exactly one polynomial. So the polynomial that we are considering is degree k minus 1. There's exactly one polynomial of degree k minus 1, exactly one, that on k distinct values take some arbitrarily given k values. So, so just set d to be equal to k minus 1, and these two facts are exactly giving you that k. They're just saying that if I given gamma and beta, there's exactly one alpha, which will satisfy that a of alpha at gamma j is equal to beta j. And because there are 1 over f to the k, the f to the k alpha, that they were chosen uniformly at random from all these 1 over f to the k sides. So this probability on the left is exactly equal to probability on the right. And now it just follows, the middle equality just follows because you just marginalize out everyone, all the k minus 1 things, you get that each single one of these probabilities is 1 over f. So the middle one just follows. So yeah, so the crucial thing is that this is actually equal to the uniform distribution, so and hence it's also independent. So just radius that in this case. And basically the point is that there is a unique alpha for which a alpha gamma is equal to beta j for k gamma k indistinct. So this fact we didn't prove, but it's a standard fact. It follows from the fact that Vandermonde determinant is non-zero when the columns are distinct. You must have done it in class 12, I'm pretty sure. At some point there. So you will just leave it for that. And after that, this claim is okay. So, but how does this fit in our thing? Firstly, all these fields for now are rather abstract, like they just happen. So, I was pointing out, how do we make these computations? Second is, it's not quite what we want, right? So, even if we could somehow compute over the field, there's some field f of some size, and we are getting uniformly random element from that. What we need is uniformly random signs or uniformly random bits. So, if we somehow take these random things, elements that we are getting from the field, and make them into bits. So maybe the two things you can think of is what kind of field should we choose so that this is easy. And next time I will show you some code also implementing this, and also what can go wrong converting theory to practice. So engineering is an important thing, and we'll see one example of how it can spoil. Not engineering things properly can spoil nice theoretical things, or not as much advantage as a theoretical guarantee would claim. So that's the end of the class for today. You'll be stopping in the middle sort of because I wanted to show you the code today itself, but we'll do it on Wednesday. So any questions? So the homework is up. The deadline is I think what I forgot to do is to write down that late policy. So the late policy is okay. So there will be 5 homeworks, best out of which 4 best will be taken for the grade for those of you who are creating the course, and also again for those of you who are creating the course and will submit the homework. Overall, the 5 homeworks there will be some 7 days of late submissions. So you have 7 total days, and you can distribute them however you want among the 5 homeworks. So the deadline for this one is March 8th, and you can submit it on Academy. It should be you can see the link. Okay, so that's the administrative part. So any questions? Yeah, if not, then okay. So we'll meet on Wednesday. I'll just upload these notes right now and to Academy. You can also ask questions there. So there's a queries section for each lecture. You can just add the queries. There's also some question from Swagato about concentration. So that's an interesting question. So I will encourage you to look it up in the last class. Yeah, so we have only touched scratched the surface of concentration inequalities. There is much more, yeah. So one reference is, so there are many books devoted to concentration. There's a book by Boucheron, Lugosi, and Mazat called Concentration Inequalities. In terms of applications to statistics in high-dimensional algorithms, there are these two books, one by Martin Wainwright and the other by wait, yeah, so it's another called probability in high dimensions. Yeah, Roman version, yeah, Roman version. And I think they're both, so they're books, but the lecture note from which the books arose are available from the author's website. So you can also, yeah, I'm pretty sure I think these are also mentioned in the description section of the course. So you can also go and take a look there. There's one. The second one is version and Wainwright. So the last two books are more considered. The first one is probability in high dimensions, the second one is statistics in high dimensions, but they also have a very good treatment of concentration inequalities and with an eye towards application. So it doesn't become too dead. Of course, I mean, concentration of a measure by itself is a very interesting subject. So there are books just devoted to that in various subjects. So the first one is more like that. That also has a lot of application, but it's more focused on techniques for concentration. The second two are more focused on applications to probability statistics, but also have a very nice discussion. So the one of the first version in one is called high dimensional probability. Wainwright one is called high dimensional statistics. So I think the lecture notes from which they arose are also available from the author's websites. So you can also have a look at those before you look at the course. Okay, so that's all for today. Thanks.